Hey, and welcome to my talk on the complexity of drawing a graph in a polygonal region. This is joint work with Anna Lubio, who you can see here, and Jyoti Mondal, you can see here, and I'm Till or Tilman Milso. And yeah, welcome to my talk. So what is this talk about? We look at the following algorithmic problem. You've given a closed polygonal region, here indicated with black, and some planar graph, here indicated with red. It's just a tree. And some of the vertices of this planar graph are attached to the boundary of the closed polygonal region. And what we want is we want to have a drawing of this graph inside this polygonal region. Note that since this polygonal region is closed, it might be that part of our drawing is on the boundary of the polygonal region. Here, this is a hole. Okay, so that's a problem that we studied, and that is this talk is about. So yeah, I will start with some motivating why we want to study this problem. I think in general, there's a whole community of graph drawing people, and what they're interested in is they have given an abstract graph, here I just drew it in a silly way, and then they actually want to draw it. So it's a very natural variation of this very basic problem to just say, okay, I want to draw this graph, but I want to draw it in a polygonal region. Okay, so there's more motivation for it. So we can think of an architect who wants to build a building, right? So he's like, oh, I have this plan, I'm gonna build this huge airport. But then in the middle of it, this guy comes and says, oh, well, we know you already built this, but now we have completely other plans. Can you still manage it? And then you're like, oh man, that's super hard. While maybe before it was easy to plan this building and to build it, now it becomes much harder because in the middle of the process, you've done part of it. Now you have to finish the rest, but in a different way than you planned. So how is this metaphor related to our problem? Let's look at this problem called planar drawing extensibility. So you've given this input graph, and you already started to draw something, but right, this is maybe what you started already, like the part of the airport that you started, but maybe the planar graph that you given is not the planar graph that you had originally in mind when you did this partial drawing. And now you have to finish it to a plane drawing. So this is a motivation for studying this. This architect metaphor is a motivation for us, and we generalize this planar drawing extensibility. So how do we generalize it? You could imagine for every vertex which is already drawn, we make a hole, which is just a single point, and make a vertex at that hole, fixing it there. And now, drawing the remaining graph is equivalent to making an extension of the graph that we've been given. Okay. I hope this is clear. So we take this input and make it an input of our problem by just every vertex which is pre-drawn, we make a point hole out of it and fix a vertex to be on there, and then we just want to draw the remaining graph in the polygonal region bounded by some big square around it. So this planar drawing extensibility problem was already studied and was shown in 2006 by Padrinani that it's NP-hard. But it was not known to be NP-complete, and he discussed that, well, he doesn't know how to show it's NP-complete. And it was even one of the selected open problems in graph drawing 2004, and it was not known what is the status of this, but it was considered one of the important open problems in graph drawing, and now we study generalization and we determine the complexity of this generalization. And it's kind of only like a little bit generalizing it. Okay, so this is another part of the motivation. The next motivation is for dynamic graph drawing. So what you could imagine is that you have a graph G1, which is here, and you draw it, but then maybe someone says, oh, draw this extra edge, or delete that edge, and so on, or draw this extra edge. And this continues and continues. So edges can be deleted, edges can be inserted, and every now and then you actually want to draw the graph that you're interested in. And then you want to know, oh, can I actually do it or can I not do it? Do I have to maybe delete vertices and redraw them? Or can I just insert stuff in a nice way? Yeah, I think dynamic graph drawing problem is a very natural problem if you're interested in drawing graphs and data structures, and this is the first thing to come up. And our problem comes up as a partial problem of this. Okay. Okay, so some more related work. There's too much related work in graph drawing. I mean, the kind of drawing that we suggest is just the most natural drawing, or the most studied drawing, I guess, that exists. And there's just too much. But just to highlight one specific result from William Tutt from 1963 on his paper How to Draw a Graph, he showed that for convex polygon regions and a three-connected graph, you can always draw the graph such that every face is convex and the bit size is polynomial. So that problem is polynomial time solvable. I think there are even linear time algorithms. And here is polygonal region. All it is just a convex region. So it is a special case of what we did, but for the very simple case of the region is convex. Important topic in graph drawing is also the granularity, like how close are these vertices. So there's another result which shows that you can draw a graph in n times n grid, but I don't want to go into this. But maybe now that we've seen that this problem is well motivated, let's see the results that we have. So our first result is that actually it might be necessary to use irrational coordinates for drawing the graph, although the input has only integers. So this already shows that the naive way of showing that the problem is in NP cannot work. And actually what we show is that this problem drawing graphs and polygons is actually existential or complete. This in a sense rules out NP membership, and I will explain this class in a second. Yes, and these are our results. Okay, so let me explain you what is existential or complete. Yeah, so existential R is a complexity class, and it says anything reducing to this problem ETR. ETR is a computational problem. This here stands for the class, this stands for the computational problem. And so we say existential theorem of the reals is just all true formulas. So where we ask for, does there exist real variables satisfying some formula? And then the whole thing is also a formula. So we have this certain kind of formulas where this thing here is quantifier free and it is a well-formed formula with those symbols. Okay, this is a little bit abstract. Maybe logicians say, okay, that makes sense, but if you're not a logician, then maybe the best way to see what's going on is just to see a simple example. So maybe we want to know if this equation is satisfiable and not this inequality. Like, does there exist real numbers such that this equation is satisfied, but not those, but not this inequality. Yeah, so in general, it's kind of solving equations and inequalities, polynomial equations and inequalities. So here, for instance, we have x squared, but that's just a shorthand notation for x times x. And here we have minus, which isn't allowed. But there are some tricks that you can simulate minus in a clever way with inserting some additional variables, and also 12 should be regarded as 1 plus 1 plus 1 plus 1 plus 1, and so on. Yeah, okay, so now you know the definition of existential R, but why is it interesting? Why do we care about it? And it's a little bit sometimes referred to the real number analog to NP, or just the real analog to NP. And we will see what that means, or maybe give now a short explanation, which is just in NP we have Boolean variables, now we have real variables, and instead of just Boolean operators, we have arithmetic operators and Boolean operators. Okay, so why is this important? So first, maybe let's note that existential R contains NP kind of trivially, just because it's more powerful, more expressible. It's a non-trivial result that it's contained in P-space. And of course, we don't know if any of those inclusions are proper, because if we would know if one of those inclusions would be proper, we would know that NP and P-space are different, but we don't know if they are different. So we cannot expect to know. We cannot expect soon to get a proof that this inclusion is proper, but we get some in-between complexity class. Yes, and let's see why this is important. Why is NP important? Because many problems that you would think of maybe are in NP actually existential are complete. And let's see one of those problems, which is recognition of segment intersection graphs. So as input, you get a graph, and you want to know, can I represent it as a segment intersection graph? So every vertex is represented by a segment, and if two segments intersect, they should have an edge in between. So this orange segment represents the orange vertex and intersects the light green, dark green, turquoise, and light blue segment. Light green, turquoise, dark green, blue segment. Wonderful. So this segment representation represents this graph. And what people thought about it, so this is just the definition, so what people thought about this problem is this problem in NP? And because of some perturbation argument, you would think, oh, it's easily shown to be NP. We know integer coordinates of phi is probably those coordinates shouldn't be too large. So yeah, so the problem is recognition segments on NP, and Jiří Matušek commented on this, and he said, well, people seriously conjectured that the number of digits can be polynomially bounded, but it cannot. So people thought, oh, maybe you just need to specify these coordinates, and probably you don't need so large coordinates. But this turned out to be wrong. So this kind of naive idea, which is very natural, it's not true. So you actually need exponential number of bits to represent this. So this is crazy. And actually turns out that problem is existential R complete. So this is a kind of a common phenomenon, which now we showed also for our problem. And actually, for a bunch of problems, now we know they're existential R complete. So it's not an isolated phenomenon, but actually it's really kind of a trend, a hot topic in computational geometry. So for instance, recognition of unitist intersection graphs, minimizing the number of crossings for a given graph. The art gallery problem. So the art gallery problem, this was kind of an important step, because I think people really didn't expect that the art gallery problem is ER complete. And here the proof that it's ER complete, it was also the big step forward for our results. So we heavily rely on the techniques developed to show that the art gallery problem is complete in this paper. Very famous stretchability of pseudoline arrangement. So you've given a pseudoline arrangement and you want to represent it by straight lines. Another ER-complete problem. This shows that the expressibility of line arrangement, like what we can do with it, to recognize this combinatorial structure, is really more difficult than for usual discrete problems. So geometric problems seem really to have these connotations with real algebra, which you would not expect before. So let me give you two more problems: visibility graph recognition and Steiner's problem for polytopes in 4 dimensions. So here you have given abstractly a polytope and you want to realize it. So all of those problems have a similar problem, flavor, and they're all extents are complete, which makes this complexity class an interesting complexity class. And now we have one more member, namely drawing graphs in a closed polygonal region, right? Which is a very natural problem. Okay, so for remainder of this screencast, I will show you the proof of the result that I have stated. If you're not interested in proofs, now is the time to switch off. So first, let me talk about irrational coordinates. So this result heavily relies on a result that I have with Mikhail Abrahams and Anna Adamaszek. So we showed that for guarding a polygonal region, namely this polygonal region, you need 3 guards with irrational coordinates. And this example we used to show that also drawing a polygon drawing a graph in a polygonal region also needs irrational coordinates. So let's go back to these irrational guards. What did we do is we forced 3 guards, GL, GM, and GR, to lie on these 3 lines using those pockets here. And then we could show that GL and GM needs to see together these 2 pockets, and GM and GR need to cover those 2 pockets. And so this means for GM it must lie behind this curve CR and behind on the right of CR and on the left of CL. So we can compute this curve CL and CR, they intersect at one point, and coincidentally the green line also intersects at this point, and we can actually compute this intersection, and it turns out it's an irrational number. And now our proof idea is for these vertices, for our graph drawing problem, to make this a graph drawing problem. So how do we do this? We just replace every guard by a vertex, and all those things here, these boundary segments, we also replace by a vertex. So whether a vertex, 2 vertices see each other, or I can draw an edge in between, it is a kind of the same. It's not quite the same because, as you see here, we might end up with crossings, which we don't want, right? But we can handle that. So we have to see how can I force a vertex to lie on a segment, right? This is what we did here. We forced this guard to lie on a segment. So to do this, we just have this little gadget here. So kind of obviously this vertex needs to be connected to this vertex on the boundary, so it needs to lie on this segment in order that it can connect, or it lies in here, but this cannot be because it also has to be connected to other stuff. So now we have this variable segment, and we just replace every vertex by this variable segment, every guard by a variable segment, and now we get 1, 2, 3, 4, 5, 6, 7 of these segments, and suddenly we have a graph drawing problem very nicely. And in order to remove this crossing here, we have to insert a hole. So we don't know what's going on. We are not allowed to have holes. Would be interesting to see. But yeah, using this hole, we force everyone, and then everything stays the same. So all relations stay the same, and that's why there is again a unique solution, and this unique solution for irrational vertices. So that was this. And now we carry on to showing that the problem is existential or complete. So how do we show this? We reduce from planar ETR-inf, for this planar ETR-inf. It's a special version of ETR. So we have real variables, and we have following type of constraints: setting a variable to 1, having addition constraints, and inversion constraints. That's why I called ETR-inf. And we also want that all variables stay in the range 1/2 to 4. Okay. Yes. So, and we want to have that the variable constraint graph. So we have a graph between all variables and all constraints, and we even require that this graph is planar. And yeah. So we first show that this problem planar ETR-inf star is complete. And we just reduce from ETR-inf and ETR-inf, and then we replace crossing. And ETR-inf was shown to be accidentally complete in this Arxiv paper. Okay, so what do? We want to replace crossing. So we take this graph in ER-inf, we draw it, and we get some crossings, and then we replace crossings by this thing. Ideally, we would like to have a gadget to replace crossings. So what is this thing doing? It has x and x prime, like we want to go from x to x prime, we want to go from y to y prime, but there's kind of a crossing. So we want to get rid of the crossing. What can we do? Instead of the crossing, we would maybe insert this thing. So here x goes into this addition gadget, y as well, and then z must be larger than x plus y, and z is smaller equal to x prime plus y. So because y is the same and z is the same in these two, actually x prime must be smaller or equal to x. And by the same argument, y prime must be larger or equal to y. So it's not really what we want, it's just a half crossing. It's halfway where we want to go. It doesn't enforce what we want. We want to get a real crossing gadget. But what we can do is we can use this half crossing gadget, combine it, use 4 of those, and we get an actual crossing gadget. So what happens here? So we split x. So x here must go larger. So x prime must be larger or equal to x because we have 2 of those half crossing gadgets. But then we here also x has to be smaller or equal to x prime because again we use those half crossing gadgets. And in the end, it turns out that x must be the same as x prime, and the same happens for y and y prime. So now we have a crossing gadget. We replace all the crossings, and we have that this planar ER-inf is also ER-complete. Great. Next step. Now we can use this, and we have to show how to reduce from planar ER-inf. So first step, how can we include variables? We already showed this. We have this variable gadget here. We interpret these two values as a half and 4. Anything else by linear interpolation, and we will just represent this this whole thing just in green here, and we will assume that we can always draw a little hole which enforces us for this vertex to lie on the set. And then now we have to copy variables around to go to the specific gadgets. How do we do this? Well, again, let's just do a half copying, right? So we have here variable segment, there variable segment. It's easy to see because of the intercept theorem or Thales theorem that here x is smaller or equal to x prime. Note here that it's flipped between here x prime is encoded in a different way as x. It's just flipped upside down, where is a half and where is 4. Now again, we can combine 4 of those those gadgets, which enforces that x is smaller or equal to y and x is larger or equal to y, which ensures in the end x equal to y. So now we can copy variables around. Great job. Next, we might want to use variables at different places. So what we can do is we can split a variable. We just attach 2 copy variables to one variable or to one vertex, and now suddenly we have the same value twice in another. Right. Next thing, we might need turnings. It's a little bit tricky, but what we do here is we have some relation between x and z1. And z1 and y. Let's look a little bit at this. So this relation between x and z1 and y, it's the same function. So we know z1 must be smaller or equal to some f of x, and we also know that y must be larger or equal to some f of z1. That z1 must be larger or equal to some f of y. But it's actually, for those 2 gadgets, it's the same f because these 2 gadgets are just mirror copies of one another. And because it's the same f, we actually get that z is smaller or equal to f of z1 and f of z1 is smaller or equal to y. So this implies x smaller or equal to y. And on the top, we do it the other way around. And that's why we also have, so here x smaller or equal to y, x larger or equal to y. So this implies that x must be to y. equal to y. Great, so now we have turns, and here you see where we need turns. We want to encode maybe a variable in a horizontal and a vertical way, so we need turns, and then this is a very simple inversion gadget. You can see if the things would be tight, then you would see that x is the inverse of y, or y is the inverse of x. This you can see because these two blue triangles are similar. But if our hole here is below, then x times y could also be larger or equal to 1. So y could also be larger than the inverse. And here it could be smaller or equal to the inverse. So now we have an inverse, the two inverse gadgets that we need. And it remains to have an addition gadget. And here we use the same addition gadget as for the art color problem. So as I said, we heavily rely on the proof of the art color problem. So we encode x, y, and z on these three variable segments, and they all need to be connected to this vertex u, which we somehow force to be below this hole here. And then the only way that x, y, and z add, so that x plus y equals z, so we assume here, first for the purpose of this proof, that z is not here, but just at the extreme example, is if x plus y equals z. So how do we prove this? So we do the thought experiment. Let's say we move x by some distance. And what we want is that z moves by the exact same distance. And we can show this because of symmetry between x and y. We've shown that this is actually showing addition. So let us show this. So let's look at this t here. If you look at this point, then you see that this t is exactly half of the distance that z travels. So we need to show that the distance that x travels is half of the distance that this t is. This distance is twice t. So let's try to show this. So what we do is we just define some distances here. So from y to the start of t, we call a. To the end of t, we call b. So easily seen, b minus a is t. And then from the start of y to where x started is a prime, and where x ended is b prime. It's easy to see a prime minus b prime is d, and b minus a is t. So now what we have to show is a prime is to a and b prime is to b. So let's look here at u. So we have, from u we have this distance here, and this distance here must be the same, because this distance AB is the same as the distance BC. So therefore, it's kind of, this distance must also be the same as this distance, as you see. And thus, A prime must be to A, and for the same argument with U prime, B prime must be to B. And then we see D equals A prime minus B prime equals 2A minus 2B equals 2T, and we're done. So it's actually a very simple geometric proof, and it's kind of a little bit unintuitive, and it's not quite clear why it works. So you need a certain distance to be equal, but yeah, somehow we randomly found this gadget and it works. So yeah, but it's nice. Okay, and now we have to just combine this part. So we start with the drawing of our planar ETR-inf graph, and then replace all the edges by these copying gadgets. These addition gadgets we replace by, the addition constraint we replace by addition gadget. Corners replaced by turning gadgets, and here we might also need turning gadgets inside this inversion constraints. Okay, and that's it. And I thank you for your attention. And yes, this again was joint work with Rubu, who apparently okay, never mind. Okay, thank you.